conservation of mechanical energy. So the conservation of mechanical energy means that the total energy, mechanical energy, is always conserved. Of course, one form of energy can be converted to the other form of energy, but it cannot be destroyed, or we cannot create energy and we cannot destroy energy. So for example, in our previous section, we talked about the work done by the gravity, and we will use the same example here in this case as well. So we have here, we have an object which was initially at point A, and then we raised it to a point B. So we have, this is y-axis, we have z-axis, and then we have x-axis. So here, so this is on the xy plane, xz plane here, and this here is so to give you just some feeling that it's in the 3D. And now the difference between A and B is h. And we want to know that how is the energy conserved in this case. If we, for example, bring an object of mass m from point A to point B. So we want to see that how is the energy conserved when we move an object of mass m from point A to point B. So we will see that how is the kinetic energy and the potential energy both conserved, which is the mechanical energy. So if we write in terms of this y-axis, so then we will get mg y of b minus mg y of a. So this distance, is equal to, so this h is equal to b minus a. So this is this distance, and this is equal to the kinetic energy at point B minus kinetic energy at point A. And this expression that we got when we were talking about the work energy principle. So the change in the kinetic energy means there will be a change in the potential energy. And now if we bring this B's on the one side and A's on the other side, then we will get mg y of b plus kinetic energy at B is equal to mg y of A plus the kinetic energy at of this object at point A. And now what we see here, that this is the mgh. So this is the potential energy. So as we know that this part here, so mgh is the potential energy. So we can now write that this is the potential energy at point B plus the kinetic energy at point B is equal to the potential energy plus the kinetic energy at point A. So what we see here, that this is the relation for the conservation of energy. So the potential energy of this system at point B and the kinetic energy of this system at point A is equal to the potential energy at point A plus the kinetic energy of this object at point A again. So the individual kinetic energy or the individual potential energy may change, but the total energy is always conserved. So this is called the gravitational potential energy. So why is this called gravitational potential energy? Because we use the only force that's used here is the gravitational force. And this is because this is also called the conservative force. In the conservative force, the potential energy, the energy can be stored when the position is changed. For example, when we change the position from point A to point B in the field, then we will have the energy that will be stored. And now we want to explain this conservation of energy with an example, and we will take the example of the roller coaster. So we have a roller coaster, so it's like this. So if we, for example, we have a rolling ball and we just let it go, so it will go like this, and it will come again here, and then it will go like this. And now, using this example, we want to understand this conservation of energy. So this is point A. Now at this point we have point B, we have point C, we have point D. So at point A, so this is the total height. So this is the total height, and here we have some height here, so we just call it Y, and here we again have some height which is in the y direction, At point C, we do not have any height here, and the initial velocity is 0. So the velocity is equal to 0 here, and the velocity at point B is not 0, so it's greater than 0, and this is maximum here. So the velocity, so when we let this ball go, so it will gain some kinetic energy, so the velocity will increase from 0, and then it will be maximum here, and then it will go up, and it will go like this. And now we want to use this conservation of energy relation for this system. So we have point A, then we have point B, we have point C, and we have point D. In their case, in this example, we had only point A and we had point B. So we want to write, so the potential energy at point A plus the kinetic energy at point A. So it must be equal to, so the total energy, the mechanical energy at point A must be equal to the mechanical energy, which is sum of the potential energy and the kinetic energy at point B. So this will be equal to potential energy at point B plus the kinetic energy at point B is equal to, and now C, potential energy at point C plus the kinetic energy at point C is similarly the potential energy at point D plus the kinetic energy at point D. And now we want to see what's the potential energy here. So we have the maximum height here, as we know that the potential energy is mgh. So we have the mass of the object, we have the gravitational acceleration, and we also have h. So this part is not 0 here. But here, what we see here, we have the velocity is 0. And we know that the kinetic energy is equal to 1 over 2 mv squared. So if the velocity is 0, that means at point A, the kinetic energy is 0. So this part is definitely 0. And now at point B, we have some height, so the kinetic and the potential energy relative, the potential energy of this object at point B is smaller than it was at the point A, because the h is smaller, this distance, the height is smaller, but it's that energy, so we do not lose that potential energy, but that energy is actually converted to the kinetic energy. In this case, here the kinetic energy was 0, but now this object has some kinetic energy because it has some velocity. So that potential energy is converted to the kinetic energy. So we have smaller potential energy at point B, but we have greater kinetic energy at point B relative to point A. So we have potential energy and we have kinetic energy at point B. And now we want to know what's the total mechanical energy at point C. So at point C, we can clearly see that we do not have any height. So if we do not have any height with respect to the ground, that means we have the potential energy that is 0. So if the potential energy is 0, we have the maximum speed here. So if we have the maximum speed here, we have the maximum kinetic energy in this case. So at point C, the potential energy is 0. And now again, this object will go like this here. It will be at point D. So at point D, we again have some height, and it will also have some kinetic energy because it's lower than the point A. So we will have again the potential energy plus the kinetic energy. And this object, this ball, will go like this, and it will, if in the ideal case, if we ignore the resistive forces, the frictional forces, and also the air drag, then it will go to exactly the same height as the point A, like this here. It will reach at this point, and this is because the total mechanical energy is always conserved, and it cannot go any higher than this point. If it goes higher, that means that we have generated or we have created the energy, which is not possible, which is against the conservation of energy. And if in the ideal case, if there is no friction, it will not be lower than this point. It will always be exactly at the same point, because we have the energy that is always conserved. But in the real case, we always have the frictional forces, and we also have the air drag. So the frictional force, and since the frictional force is not the conservative force, so once the energy is converted or taken by the frictional force, we cannot get it back. So that's why in the ideal case, due to the loss of energy due to the frictional forces, the ball will always go like this, but it will be little bit here. It will go like this, and it will go down like this. So this is the conservation of energy. And now we want to know what is actually the gravitational potential energy. We talked about the gravitational potential energy here when we were talking about the conservation of energy, but we want to know what is actually the gravitational potential energy. We talked about the kinetic energy, but we want to right now know what is the potential energy. So the gravitational potential energy. So the gravitational potential energy. So the gravitational potential energy, for example, we have the Earth. So this is the Earth, and it's attracting the objects because of the gravitational force. And if gravitational potential energy is, if we have a small mass, if we have, for example, a small mass here at point P, and if I bring this mass from the infinity to this point when it's feeling the gravitational and we have, for example, the infinity somewhere here. Infinity means we are far, far away from the Earth, and we do not feel the gravitational potential energy or the gravitational force because we are far, far away from the Earth. Or
to give you some idea of this infinity, imagine two magnets. If these magnets are close to each other, you will feel a strong force because the distance between the two magnets is very small. But if you move these magnets away from each other, you will feel a smaller force. But if these magnets are far, far away from each other, they will not feel any force. This is the same thing with the gravity. Since the gravity is attractive forces and it's a property of the mass, if the two masses are very close to each other, you will feel the gravitational force. But if they are away from each other, then the gravitational force will fall off 1 over r square. But since the mass of the Earth is extremely high, that's why when we are very close to the Earth, we do not feel this difference. But we are talking about thousands of kilometers here in this case.
Any object, it can be any object that has a mass, because the gravity is the property that's related to the mass. So we are far, far away from the Earth, and we bring this piece of mass, which has a small m, and for the Earth we use big M with this sign. So this is the mass of the Earth, and we have the small test mass, small mass, and we bring it I bring it from the infinity to this point where we feel the gravitational force. Now the work done, that is done by me when I took this object from infinity to this point, that work done is actually equal to the gravitational potential energy. Now you can say that, how do we calculate? How do we know how much work done I have done? So it's the same work done as work is according to the Newton's third law. It's same as the work done by the gravity. So my work done, my force will be like this. So this is I have applied the force, so I can say a person, or the gravitational force will be like this, gravity. So but they will have the same the work done will be the same by me or the gravitational force. But now we want to know what is the gravitational force. So first we want to explain, we want to define this gravitational force. So for that we need to explain the Newton's universal law of gravity. So we will come back. For example, we said that the gravitational potential energy is when I bring a small mass from the infinity to the point B, and that the work done by me or the gravity is equal to the potential energy. But we know that the work done is equal to the mass, the force, and the distance that is covered. So we know what is the distance. For example, we call it r, but we want to know what is this force. That's why we are first talking about the force in this case here. So according to Newton, so the force, so the gravitational force. So if we have two objects, where one is here, one has a big mass and we have the small mass, so it can be two objects. So this object will feel a force, so in this direction. So this is the F, small m is feeling a force because of this big M, big mass, and it will also feel the force which is big M, is feeling a force because of the small m. According to the Newton's third law of motion, so this force and this force must be equal. So action equals minus reaction. You can see that they are equal but in opposite direction. But we want to know what is this force. So this force of the mass small m is feeling because of the big M is equal to the mass of the small m multiplied by the big M and the gravitational constant and divided by the r square. So the r is the distance between the two objects here. And this g is a very small number. So this g is equal to 6 into 6 multiplied by 10 raised to power minus 11. So this is, we can see here in the standard SI units. So this is extremely small number. So according to, as we said, according to the Newton's third law, so this object will also feel a force because of the presence of this object. So the both will feel a force, attractive force. The gravity is always attractive. So they will feel an attractive force, and this is called the gravitational force. And Newton has defined it as the mass of the small object or mass of the one object multiplied by mass of the other object. And then we have the gravitational constant, and it falls off 1 over r squared. So we know that this is extremely small number. If we, for example, we have two objects, two masses, this is 1 kilogram and this is again 1 kilogram, and this distance, the r, is 1 meter. So we have the mass 1 kg and we have another mass that is another kg, and if we want to calculate the gravitational force that they will attract each other, so this will attract a force because of presence of this one, and this will also attract the force, equal force but in opposite direction. And if we calculate using this formula, so we have 1, and we have 1 here. If we put these values there, so the gravitational force is equal to 6 into 6, so we have only this one here, so we will have 10 raised to power minus 11 newtons. So as we can see here, this force is extremely small force. That's why we do not feel this gravitational force in our daily objects. For example, I'm standing here. If I'm standing here, I have some mass, my body has some mass, and this wall or this board has some mass. I do not feel this force. But in the case of the Earth has extremely high mass relative to my body, so I feel this force which is much larger than the regular objects. So now we know that the force, the gravitational force, according to the Newton's universal law of gravity, and which is, by the way, also we can call it the Newton's fourth law. So in some books you will find that it is also known as the Newton's fourth law. So we talked about the Newton's 3 laws, and now this is the universal, the gravitational Newton's universal law of gravitation is also in some books known as the Newton's fourth law of motion. So we have here small m, the big M. So usually it's because of the Earth. Otherwise, in the general term, you can also say that the mass 1 and mass 2 here. So for the Earth, so it's divided by r. r squared. So, and we also know that according to the Newton's second law, the force is equal to the mass of the object multiplied by the acceleration. So according to the Newton's law, so we can also say that this force is equal to multiplied by the ma. So it's equal to the mass multiplied by the acceleration. So we can cancel these two, the small m's, but if we are on the surface of the earth, then we can also say that this acceleration here is equal to the gravitational acceleration. So the acceleration that is because of the gravitational force. So now we can say that the G is equal to big M, so which is the mass of the earth, we have the gravitational constant, we have the R. And now what we see here, as we have already discussed this in our previous lectures, but now from this equation we can also see that the gravitational acceleration, which we usually define as at the 9.8 meters per second squared, is not actually constant. It actually depends on the R. If we are moving away from the earth, so the gravitational acceleration will be lower, and the force will also, we can see here, it depends on R squared. So the G depends on R. So it's not actually constant. The one that we use is actually close to the surface of the earth, which is 9.8 meters per second. If we change this distance here, then we will have the smaller. If we go up, for example, on the surface of the earth, so on the surface of the earth, for example, on the surface of the earth, so this gravitational force is equal to small mass. We have the big mass, so the small mass can be any object, for example my body or anything, and then we have the gravitational constant, of course. So we have the radius of the earth if we are on the surface of the earth. So the radius of the earth, so we use usually this sign here for the earth. So as we know, this is equal to mg, and the g we can write as mg, but now since we are on the surface of the earth, so if we use the same thing here, then this is 9.8 meters per second squared. So this applies only for the surface of the earth. And now we know, since we were actually talking about the gravitational potential energy, since we are talking about the gravitational potential energy, and we said that we want to know what is the gravitational force, and now we know what is this gravitational force, so we come back to gravitational potential energy. Gravitational potential energy. So what we were talking about, that gravitational potential energy is, if we, for example, this is the earth which has a big M mass, and I bring something as a small mass to a point P from infinity. So this is somewhere infinity. Infinity is far away from the earth, and it's far away, and we do not feel this gravitational force. And we bring a small mass, so this is a small mass which has a small m, and this is point P. And the work done that I have to do to bring this mass from infinity to this point where this small mass is feeling the gravitational force in the presence of this earth. And that force, the work done, so we said that this is the force, for example, done by me, Talha Nisar, and then we have the gravitational force. So we were actually talking about the gravitational force. So now we know what is this gravitational force. So we can talk about, so we said that the potential energy is equal to the work done, that is done by me Tn Talha Nisar, so which is the force multiplied by distance. So, or it's also is the force by gravity, this distance, and this is the r. R, in this case, this is the d is the r here. So we will again write, so the work done, that is done by me Talha Nisar, is equal to plus, so if we take my force as a plus, so automatically the opposite force will be minus. So in the gravity is doing a negative work because I am doing a positive work, because the minus sign only represents the direction. So we have a small m, we have a big M again. So this is the force that is done by me. So we have a small m here, and we have a big M which is for the earth, and we have the distance which is from here to here. So this is the force that I needed to do because of the because I bring it from the infinity. And now the work done from infinity, done by Talha Nisar from infinity to point B, is written as the minus, since it's opposite direction, we have the m, small m, divided by r. So this is the potential energy. So this is the gravitational potential energy, and this gravitational potential energy is zero at infinity, because we do not feel the gravitational energy. For example, if we put infinity here, infinity, anything divided by infinity is equal to 0. So the gravitational potential energy is maximum, is 0 at infinity. Now, if we want to plot this equation here, so for example, we have the so this is the potential energy. This is the increasing, since we have a minus here, so we will have, so this is the r. So r is in this direction. So we are moving away from the earth. So here is the radius of the earth, so this is a 0, so this is the radius of the earth, and this is a point A, and we have the point B. So the distance between these two is h. So the force that we will see will be like this. So it will go like this, will be close to like this. So the potential energy, as we can see here, as we go to infinity, so infinity is again somewhere here far away, so this potential energy will be 0. So at point A, so this is the surface of the earth, so we will use the radius of the earth. So this is the radius of the earth. So this is the r of the earth. But if we want to include this, then we will have the r plus h here. So for h equals h is much smaller than the radius of the earth. In this case, when we are, for example, we are on the surface of the earth, on the top of the surface of the earth, the distance from the surface of the earth to any point is much smaller than the radius of the earth. This is what it means. So from here to here, we have the radius of the earth, and then we have the height, and then we go to infinity, and the potential energy is increasing. So this is how we plot this equation here. So the potential energy at point B minus, so this B minus the potential energy at point A is equal to mgh. So this means that, for example, I am on the surface of the earth, so this is a point A and this is a point B. So this is actually the height. So this is the height between these two. If you want to know what is the potential energy between these 2 points, so we have a reference point here A and we have a reference point B. So this is what it means. So we have a potential energy at point B, which is here. So in this case, we will take point, for example, point A here and then point B somewhere here. So 2 different points away from the earth. So it can also be on the surface of the earth, or it can be away from the earth. But if we go far away from the surface of the earth, means we go to the infinity, then we will not feel the gravitational force. In that case, the potential energy will be zero. Now, since we talked about the potential energies, the kinetic energies, and the mechanical energy, the conservation of mechanical energy, and now we want to know what will be the kinetic energy that will be required for a body to actually leave the earth. For example, we have here, we have the earth here, as we said that if we go far away from the earth, we will not feel the potential energy or the gravitational force. So we have, for example, again, the earth, which has a big mass here, and we have a small mass here. This is a small mass. What will we do? So how much kinetic energy is required to bring the small mass to infinity? So this is infinity. Infinity means that we are far away from the Earth's surface, and that far away that we do not then feel the gravitational, or it's extremely small. It's extremely small or close to zero. So we do not feel the gravitational potential energy or the gravitational force. So what will be the kinetic energy? But we know that the kinetic energy is equal to 1 by 2 mv squared. So actually the m is constant, we know the m, and we have the only is the velocity. And that velocity is known as the escape velocity. If we throw something with the escape velocity from the surface of the earth, that's the initial velocity, it will leave the earth for hour and hour and hour. It will never come back. For example, if I throw something if I throw a ball upwards in the sky, it will come back to the surface of the earth. Because of the gravity. But if we throw something with the escape velocity, it will never come back. And we want to know what is that escape velocity. So now, escape velocity. So we have the radius of the earth. So this is the radius of the earth. So we said that we need to know what is escape velocity, v escape. So what should be the velocity that should be given, the initial velocity to this object, that it should leave the earth and it just reaches the infinity where it does not feel the gravitational energy, and it actually stops somewhere here. So the initial velocity, the final velocity should be zero. So the initial velocity is the escape velocity. It will be decreasing at the infinity. It will be zero. It stops there. So we will use the mechanical energy there. So we have the mechanical energy or the conservation of energy. So we know that 1 by 2 m escape velocity squared plus, and we have this potential energy here. Potential energy is minus small m, the mass of this object, and then the mass of the earth divided by radius of the earth, which is represented by r, big R, and then the g. And this is on the surface of the earth. So this is the mechanical energy. Mechanical energy, as we discussed, that it's the sum of the kinetic energy and the sum of the potential energy. So we have the kinetic energy, which is with the initial velocity, it's not zero. And on the surface of the earth, here in the beginning, we have the potential energy here. So it must be equal to this is, for example, a point A, and then we have a infinity there. So at infinity, we also want to know what's the kinetic energy. So kinetic energy plus minus, so this is minus m g again r. So this is the different r. So this is not the radius of the earth, but it is the distance here. So this is the distance here. So as we said that, so at infinity the potential energy is 0, as we have already discussed here. So this part is 0 because this r is infinity. Anything divided by infinity is 0. And as we said that infinity, the velocity, whenever we throw something up, the velocity will go down and at some point it will go back. But here the velocity is decreasing and it reaches the infinity. At infinity, since there is no potential energy, it will never come back, but the velocity is 0 here. Since the velocity is 0 at infinity, this term is also 0. So what do we get? So we get 1 by 2 m escape velocity squared minus m divided by radius of the earth is equal to 0. So on this side we have 0. And now this is, we can make this 2, we can bring this one here. So we will have 1 over 2 m escape velocity squared equals m divided by r. So this is we get. So what we can do, we will bring this m here. So first of all these two cancels, and then we bring this 2 here, and then also we have a square root. So we will have the escape velocity is equal to, so this 2 comes here, so from the downstairs it goes to upstairs here to the denominator, and then we have the mass of the earth, we have the gravity, and we have again the r. So this is the escape velocity. So what we see here, we have the mass of the earth, we have the gravitational constant, and we have the radius of the earth. We know that the radius of the earth, which is 6,400 kilometers. We know the mass of the earth, and we know the gravitational constant. If we put these values, so we will get, so the escape velocity is 11.2 kilometers per second. It's extremely high velocity. So, but this is only valid when we ignore the resistive forces, for example a drag force. Otherwise this is very high speed here. But in the reality, we actually, whenever the rockets are going up, the air is always a fuel that's accelerating the rockets to the orbital orbits, or when the astronauts are going to the, for example, moon, there is always a fuel. So we never apply the escape velocity. There is always a constant force that is applying because we have the gravitational force. And on the other hand, this is extremely high speed. But whenever, if we throw something with this speed, upwards, that object will leave the gravitational field of the earth. It will never come back.